All right, clocks. We have two clock sources for code execution. We have this crystal, and this crystal can be used to drive a PLL to multiply the frequency upwards. And the PLL has an option to do frequency modulation, where we vary the frequency. Instead of being rock solid 64 megahertz every time, we're going to have it varies slightly. It'll be 64 plus a percent, plus 2%, plus 1%, 64 minus a percent, etc. That kind of range. You can specify a range and how fast you want it to vary off that 64 megahertz. And what that does, it spreads the noise around, so it's not always on a fixed frequency, and that's kinder to neighboring electronics. It's a feature you have to turn on if you want to use it. And the other clock source for code execution and system clock is this fast internal reference clock. That is the default clock when we first power up 16 megahertz. And it's a little sloppy, so you can trim it. Basically, trimming involves counting to a millisecond with one counter that's fed by the crystal, because crystal's rock solid. And then you have a second counter that counts to a millisecond using the 16 megahertz. And so there will be a difference, and use this difference to adjust it. Just keep incrementing up or down until you're close to where you can be, and then that value can be stored in external flash if you like, and it's always there after that. It's actually stored in what we call a shadow section of the flash, which is just a high address in the flash area. And then we have clock sources for low power. Now, I don't think you're going to need low power for this. I'm just going to mention it briefly. Low power means we stopped code execution. Maybe we've turned off power to the flash. Maybe we've turned off power to 90% of the registers. It gets very low, tens of microamps. We're on standby power here. And so the more you turn off, of course, the longer it takes to power up. And typically you wake up either by an input signal or by some timer. So the timer can be fed by either this 32 kilohertz external crystal oscillator or an internal 128 kilohertz internal RC oscillator. Now, we have a clock monitor unit, and I'm just going to have one slide on this. The clock monitor is to measure the health of these clock sources using the information it has. So it'll use one clock source to look at the other clock source. If it sees something it knows is wrong, then it can generate either a reset, an interrupt, or transition into what we call a safe mode, which we'll cover shortly. So the first thing it does, it looks at the PLL. So you can specify an upper and lower range, and basically it divides the PLL down and knows what the crystal is, and if it violates a range, then it will holler. It will look at the crystal and say, hey, the crystal must be at least this frequency, and it'll use the 16 megahertz for a reference here, internal clock. And so if the crystal falls off, for example, it will holler. And then the other thing is, it can be used for this frequency meter to measure one clock source versus the other, and this is for trimming these internal reference clocks. So these events will generate either reset again, or a safe mode request, or interrupt request. Now, let's just walk down. This is a pretty useful diagram. It's right out of the manual, the clock sources. Here you can see on the top left in the green here, the oscillator clock. This is what we call our crystal. Can be 4 to 16 megahertz. All these boards that we're giving you have 8 megahertz crystals. And then our internal reference clock is 16 megahertz. And we can have a system clock which is either the crystal frequency divided by a number, or the crystal frequency straight through, the internal 16 megahertz divided by some number, or the 16 megahertz straight through, or the crystal going into the PLL as selected as a system clock. And again, out of reset, we're running off of this 16 megahertz. So we're going to have to select a clock, and we have a process of doing that. I'll show you shortly. The system clock then can be divided, if you want, to different sets of peripherals. And the reason we do this is for low power. We want to, not have to have the fastest clock if we can get by with something slower in many cases, you know. So what we want to do is, for example, if all your PWMs only run at 2 kilohertz, you don't need a 64 megahertz input going into it. You could divide it down for low power of, say, divide by 16. So that will, you know, give you a lower frequency. It saves you a little bit of power. Maybe not a lot, but then when you start adding these up, it will extend your battery life for those kinds of applications. We think probably for your competition, you probably won't need to bother with this. You can probably just leave them divide by 1, and it's up to you. It's your choice. Here's our clock monitor unit that I mentioned before. Here are the other oscillators that can be used to feed these timers that can be used for wake up from a very low power mode. And then we have software watchdog timer here and a clock out. And the first exercise, we'll use this clock out pin, and that will be divided down by 4, and you can look at the frequencies here and validate on a logic analyzer that yes, I'm getting the frequency I expect. So this is kind of backup for what I was telling you. This just shows a little more detail that I can use my system clock, divide it down for different sets of peripherals, and this is the register that it gets done in for future reference. The output clock out can be divided down. Here's the register I use to divide it and specify which clock I want to select to look at on the clock out pin. And then the PLL. So the phase lock loop will take a crystal frequency and bump it up according to this formula here. And so it's basically you take the frequency of the crystal, in this case 8 megahertz, multiply it by a number, divide it by 2 other numbers, and then boom, you can get 64 megahertz. There's an example in the application note on how to do this. It's very simple. I'm not going to spend time on it. You probably just want to take this code that we give you and say, okay, I'm up at 64 megahertz, I'm running. Okay, so this is for reference, more material on the clock monitor unit, and I'm not going to cover it. So that's clocks. Any questions, clocks?